Hello, my name is Logan White, and I'm an undergraduate at the University of Tennessee, Knoxville, and I will be talking about my research project of using the evolution of microstrains to model uniaxial deformation of laser powder bed fusion processed Ti-64. Before I begin, I would like to thank my mentor, Dr. Bjorn Clausen from Los Alamos National Lab, for taking me on as a student during this REU, and as well as Texas A&M for hosting me. I would also like to thank Dr. Giovanni Bruno and his team for supplying me with the experimental data to analyze for my project. I'll begin with a brief introduction to laser powder bed fusion. It is an additive manufacturing technique that fuses layers of powder together using a high energy source such as a laser to create 3D parts. The process is broken down in the first figure here. This type of additive manufacturing is popular for many reasons. Namely, this process allows for complete geometrical freedom to create complex parts such as the turbine shown on the right. Because titanium is itself expensive and expensive to manufacture using traditional methods, it would benefit greatly from this process. However, there are many problems with using laser powder bed fusion. Parts manufactured this way develop large residual stresses and a characteristic columnar microstructure during processing that can change the part performance compared to traditionally prepared material. The objective of this project is to understand how the processing and resulting residual stresses in microstructure affects the deformation and fracture of additively manufactured Ti-64. An elastic plastic self-consistent model was used to replicate the deformation of the titanium samples. An EPSC model treats a polycrystalline material as a collection of single crystals with orientations that reflect the initial texture of the material. Each texture is treated as an ellipsoidal inclusion embedded in a homogeneous medium. For every strain step, the response of each grain is calculated, and the weighted average of each crystal is taken as the response of the medium. So we have a polycrystalline material that is made up of individual grains. Each grain is embedded in the homogeneous medium. The response of each grain is calculated, and the weighted average of each response is then taken as the homogeneous medium. This homogeneous medium is then used for the next calculation of the strain step. Our samples are Ti-64 rods that were printed using the laser powder bed fusion process. 2 of the samples were tested as printed, and 2 are subjected to a heat treatment at 530 degrees Celsius for 2 hours. High-energy in-situ synchrotron diffraction was conducted during tensile deformation to track the evolution of several crystallographic planes. The image on the right shows our specimen design as well as orientation during diffraction measurements. An elastic plastic self-consistent model will be used to fit experimental data to determine material properties. The model works by evaluating the elastic and plastic deformation of individual grains to represent the macro-level deformation response of a material. On the left is the texture of the generated grain set that is used to represent the experimental data. As you can see, it has a very sharp double fiber texture along the 110 and the 102 directions. As this is a stronger texture than we were expecting, we also generated another grain set shown on the right using literature that has similar texture features but lower intensity. The response of both grain sets will be discussed. I will first discuss the modeling of the experimental data using the strong texture set. As you can see, the overall fit of the model to the experimental stress strain curve is good. However, there is slight discrepancy between the two in the yielding region. The table shows the critical resolve shear stress values that each deformation mode is set to activate. This roughly indicates the order and at what macro stress each mode should deform at. The plot on the right shows the normalized activity of the 3 deformation modes. As expected, basal activates first as it has the lowest CRSS value, and the system remains basal dominant until the very end of deformation. What is interesting to note is that the pyramidal mode activates second, even though it has the highest critical resolve shear stress value. This implies that the basal mode can accommodate enough slip in the A direction that relief in the C direction, given by the pyramidal mode, is needed before the prismatic is needed to provide additional slip in the A direction. In traditional modeling of Ti-64, the basal and prismatic systems activate before the pyramidal systems activate. The overall fit of the lattice curves is not as good as the previous macro curve. This is mostly visible in the elastic region, which is primarily decided by preset elastic tensors and does not change during the course of the model. The yielding regions show better agreement. Unfortunately, we do not have the experimentally measured 100 and 002 planes, which would show the activity of the basal and prismatic subsystems and better represent partitioning of lattice stresses and strains. I'll now move on to showing how the model response changes as a function of starting grain texture. This macro curve shows the modeled response of three different grain sets: the experimental set, the weaker literature set, and a grain set with random orientation. All three grain sets were modeled using the same parameters, and the critical resolved shear stress of the deformation modes are shown on the left here. Overall, they have very similar responses, but there is a notable difference in the yielding area. The strong texture has a shallow yielding curve than the weaker and random texture. Moving to the lattice comparisons, the overall trends match the trend of the macro curve. The elastic regions of each texture are nearly identical, but after yielding, the stronger texture varies from the weaker and random textures. Note that the 002 and 100 planes are modeled in this instance. As you can see, the 002 and the 100 planes respond differently from the strong texture, implying a different evolution of deformation modes is used. Here, we can compare the deformation modes used by each grain set. The order of activation remains the same for each set: basal first, then pyramidal, followed quickly by prismatic. But that is where similarities end. There is an obvious trend from random to strong texture. As texture intensity increases, the reliance on the basal plane also increases, and subsequently, the use of other deformation modes decreases. This is most likely due to the orientation of the textured grains, resulting in a higher basal Schmidt factor. This increases the number of grains that can accommodate plastic strain through basal deformation. This keeps the stress in other directions low and reduces the number of active slip systems until larger plastic strain is reached. This could explain why the yielding region of the strong macro curve is shallower than the weak and random grain set. Ti-64 is an alloy that can greatly benefit from the laser powder bed fusion process. However, there are many inherent issues with this process that can change how titanium parts perform. Modeling of the experimental results showed reasonable agreement on the macro scale and in the yielding region of individual lattice measurements, but larger error is shown in the elastic region. As a function of texture, the yielding region of the macro curves became shallower as texture and intensity increased. This is most likely due to the corresponding increase in basal deformation. Stronger texture allowed for more basal deformation, delaying the activation of other modes until larger strain was achieved, resulting in a shallower yielding region. I would like to again thank my mentor, Dr. Bjorn Clausen from Los Alamos National Lab, for guiding me during this project and for Texas A&M for hosting me.